Okay, welcome to the second lecture on Chapter 9. This is going to deal with the reactions, more specifically the reactions of alcohols. Okay, and we introduced those reactions, but now we're going to dig into them. Okay, so we're going to start in section 9.8. 9.8, dehydration. Okay, so different types of alcohols. We're going to start with dehydration. This is elimination, like in Chapter 8. Okay, so recall Chapter 8. We can eliminate a molecule of HX. Now we're going to eliminate a molecule of water. Okay, we said this before, but you must use strong acids to form a good leaving group. You take an OH, which is a terrible leaving group, and you protonate it to form an alcohol, which is a good leaving group. It's our fourth leaving group. We're going to see the same trend, increasing, just like we saw with elimination. We're going to see increasing rate of dehydration. Dehydration means we're losing water. It's elimination. Increasing rate of dehydration, primary, secondary, tertiary. Sorry, another R group. Okay, primary, secondary, tertiary. This is going to be either carbocation driven, primarily carbocation driven. All right, and the Zaitsev rule applies. Zaitsev rule, more stable alkene is the major product. Okay. Let's look at some mechanisms. Let's look at a tertiary alcohol, butyl alcohol specifically. PTSA is an abbreviation. We'll draw that out. Also, it's drawn as tossic acid sometimes. Okay, I'll give you the structure. Go ahead and put in our H's. We can eliminate. So I give you this, and I say, draw me the mechanism. Let me draw PTSA for you. Strongest acid you'll see, strongest organic acid you'll see. Lone pairs on oxygen. Deprotonate the acid, much like sulfuric acid, much like HCl. Proton transfer, the pKa of that H is -7. And this interaction gives the same idea, dissociation. I'm going to abbreviate this aromatic group as AR. This whole group is AR. PTSA stands for para-toluene sulfonic acid. Okay, so we get dissociation. And now, this H, just to make a point that I've circled, the pKa is -2.5. Acidic, but not as acidic as the sulfonic acid. Sulfonic acid gives up its proton. This is resonance stabilized a lot more than even a carboxylate. Okay. And now we have a good leaving group in water. Okay. So water can leave. We could have moved this down here. Okay, that's not an arrow. It's just draw it. We'll just draw it down here. And then this leaves minus water. You can show that several ways. Minus water, or you can show an arrow coming off here, say minus water. Now, again, this is just to talk about these things. This is the rate determined step. It's like it is in E1. Okay, so it's not always the first step. If protonation is the first step, this being protonation, if that's the first step, that's usually pretty fast. Okay, so even though we're talking about bond breaking of the oxygen hydrogen bond, that's a very acidic proton. That's fast. Now, breaking a carbon-oxygen bond, that's slow, rate determining step. This is another form of E1. So what do we have? Carbocation. 3 different CH3s, and there's our plus charge. We've got this, and we still have our sulfonate is the anion. Now, again, in principle, the loss of water is reversible, okay? But what can happen is this anion is not going anywhere. It's a spectator anion. What can happen is water can act as a base to give you product and byproduct. The byproduct is the protonated form of water. Let's draw that out. H3O plus. And the sulfonate. This proton is basically the same acidity as this one that we circled over here. Okay. So it's a byproduct, and you probably only need a catalytic amount of this acid just to make a point. This catalyst could help this catalyst gives the product, and then this could be your functioning acid where you can get an equilibrium exchange to get back to here. Okay, so not so important, just some extra information. Okay, this mechanism is E1. It's the same for secondary alcohols. Okay, and because secondary alcohols can form carbocations. And it's the same for sulfuric acid. Sulfuric acid and para-toluene sulfonic acid are functionally not that different. That is H2SO4, sulfuric acid. Okay, so go through all those mechanisms, all the variations of those mechanisms. Okay, if we go over this mechanism, you need to be able to work through these types of mechanisms. Let's go through one with sulfuric acid on a primary. This is an example of something you need to be able to draw out. I give you the Lewis structure, sulfuric acid. You got to be able to draw that out. Gives this product. Put some lone pairs on our oxygen. Draw out sulfuric acid nice and clearly. Let's put the lone pairs on the oxygen that we're going to deal with. We're going to deprotonate. Again, pKa -7. This is going to give dissociated types of product. This sulfonate is resonance stabilized 2 more times. Draw those out. There's 2 resonance structures where the negative charge could be on the other oxygens. Now what do we have? This is an interesting case because we almost always think about this as being a spectator. It's a really terrible base, okay? And it's an interesting case because we sort of need to we need to deprotonate with something, okay? So what I'm going to say is I'm going to let you use this as a base in this case, and I'm going to explain the reality is that there is probably water being generated. The key thing here is this is E2, right? You cannot form carbocation on this primary alcohol. It's a primary alcohol. That's important. So it's got to be E2, so you got to deprotonate with something. Truth be told, there is probably plenty of water. Sulfuric acid is not a pure sulfuric. It's aqueous, meaning it has water in there. So the reality is you probably have water in there, and you could use that as your base too. That's probably a better way to go. Water is a better base than a sulfonate. Okay, this is an exception. I'm going to let you use that as a base, but the key thing is you're not forming carbocation. Okay, E2. So that's a couple elimination examples. If you can form a carbocation, then you should. That's the rule we're going to use. Secondary, tertiary, we're going to form carbocations. Primary cannot, so it's got to be E2. Okay, so there's some more examples we can go over in class for those. Let's talk about Le Chatelier's principle. I've mentioned that in class. Le Chatelier principle. And let's look at this reaction. Very similar to what we just showed. H2SO4 gives butene, the double bond, gives an alkene and water, right? So this is an endothermic reaction. But by distilling 1-butene, the alkene product, you can drive the equilibrium. Meaning by removing this from the equation by distillation, then you can further drive the reaction. Okay? So even though the equilibrium favors the starting material, it may favor it 100 to 1, but if you remove that 1 over and over and over, you push the equilibrium to the right. Okay, so it's Le Chatelier's principle. Le Chatelier's principle helps us. A system in equilibrium will react to counteract any disturbance to the equilibrium. So if you disturb the equilibrium, then the Le Chatelier's principle says that the reaction will sort of react. Okay, so it will a system will change so that it can achieve equilibrium. Okay, so we can do that. We can also remove water. Okay, that's a common way to drive an equilibrium process. So keep that in mind. That's a principle that's important to keep in mind as to how these things work. 9.9 is something called carbocation rearrangements. Okay, so we learned about carbocations. We learned that secondary and tertiaries can form. Tertiaries are more stable. And essentially, I want you to remember as we talk about these things, what I really want you to remember is that secondaries can shift and go to tertiaries. The way in which a secondary carbocation can go to a tertiary. Okay, so we're going to show mechanisms for this. So let's show a reaction. Here we have a secondary alcohol right here. We're going to add PTSA. Again, we'll draw that structure out. And we're going to get a product that isn't inherently obvious. If we go through the mechanism and say this is the major product, it's confusing. Okay, we're going to protonate that, and we'll go through the mechanism. Okay, so it undergoes a carbocation rearrangement. All right, so let's walk through this. I'm going to start the mechanism on this one and go to the next. The beginning is the same. We need to protonate. I'm going to abbreviate as aromatic here. This is going to protonate just like we did before. Proton transfer. And we have our aromatic sulfonate. Okay, para-toluene sulfonate. So that's the same thing. We protonate. The next step is the same. We lose water. Again, you can say minus water, or you can show an arrow with loss of water. What do we get? We get our carbocation. Again, the sulfonate is there. So that's the same. First two steps. Proton transfer, PT, minus water gives you a carbocation. However, this is where it gets interesting. I'm going to redraw the carbocation here. Let's put the plus charge right here just to make it small. What's on that carbon is a p orbital, right? In the same way that carbocations are stabilized by adjacent CH bonds, now they can be stabilized by adjacent CC bonds. Okay? That stabilization, this pair of electrons between these two carbons, all of them can stabilize just in the exact same way. These sigma bonds are stabilizing that pi orbital. Sorry, that p orbital. Okay? So extending that, this can happen. Okay? This CH3 and its pair of electrons is sort of hopping over from carbon 1 to carbon 2. It's a 1,2 methyl shift, a 1,2 alkyl shift. This alkyl group and its pair of electrons. So the arrow starts at the middle of the bond. Okay, I'm going to draw this a little bigger here. CH3. Starts in the middle of the bond, hops over. So as that happens, no more carbocation at the secondary. We're going to create a tertiary. So what happens here? You now have a tertiary carbocation. So it went from secondary to tertiary. That's essentially the only kind of shift you can have. So the CH3 shifted from the 1,2. We call it a 1,2 CH3 shift. Okay, it's similar. It's similar to hyperconjugation, the stability of carbocations by CH sigma bonds. You can get CC bonds to shift. We're going to show in a second that CH bonds can shift too. So now there's a tertiary carbocation. Now what can happen is we can get two different products. This is where Zaitsev comes in. These H's, which are the same over here, these H's can eliminate. So this is our new alpha carbon. There's a beta and there's a beta. There's two different betas. And so this H can eliminate to form a less substituted double bond, or this one can eliminate with water as the base to give the major product. That water eliminates. These electrons go here, and what do you get? You get a tetra substituted double bond. Tetra. That's the major. There's a minor that would be a di-substituted double bond. Okay? You should draw that out. What would be the minor product? Take home assignment, draw the minor. So again, E1, okay, with the 1,2 methyl shift thrown in between. Okay. So let's also do a 1,2 hydride shift. Same idea. Start with an alcohol. It's a secondary. There's an implied hydrogen there, PTSA. We're going to get a sort of impossible looking product. Okay, you can't get that product simply by elimination. How do we get it? Protonation. Just like before. Loss of water. Now let's fill in some hydrogens. We have our sulfonate here. Got a secondary carbocation. And what can happen is, again, for the same reason that this CH bond can stabilize the p orbitals, it can, in certain cases like these, it can shift over. That H and its pair of electrons, so the arrow doesn't start up here at the H, the arrow starts in the middle of the bond, it's shifting over, and it's going from the 1 to the 2 position. It's a 1-2 hydride shift. Especially there, the hydride implies that it's a pair of electrons. H is hydride. It's not a proton shift. It's a 1-2 hydride shift. What does that do for us? It creates a tertiary carbocation. Again, there's 2 different H's here. They're identical. Either one of these is going to give that double bond. We've got some water to do the work. Deprotonation. I'm going to put it over here so you can, to make a point that they're the exact same product. Okay, it's just a rotation and it's a tumble in space. Okay, what's our byproduct here? H3O plus. Again, the O minus is over here. Like so. E1 with a 1-2 hydride shift thrown in between. All right, let's look at 9.10, dehydration with POCl3 and pyridine. Pyridine is an amine base. Let's show this. This is another way to do an elimination. This is just a different reagent. Net loss of water, it's still a dehydration. Okay. Phosphorus and sulfur, just as a side note, can have more than 4 bonds. We invoke d orbitals. That's probably a simplification, but we draw 5 bonds to phosphorus. Okay. 6 bonds to sulfur from time to time, like in sulfuric acid. Okay. We're going to treat this as SN2-like. At the phosphorus chlorine bond, again, there could be more to it, but let's treat it like that. SN2, we form an oxygen phosphorus bond, we kick out a Cl. And so now we've activated the alcohol by another route. Cl minus is not very basic. Okay, that's why we have this. This is a base. Okay, the amine base has a pair of electrons on nitrogen. This salt here is going to sit there until the amine is going to deprotonate. Okay, that deprotonation gives the same idea. We just have created a good leaving group. Okay, so if you want to think of this as another leaving group, it's sort of generated in the reaction, so it's not so much, but it's a good leaving group, like water. Okay, so this whole thing now is a good leaving group. Just you formed an oxygen phosphorus bond, and so what can happen is excess pyridine. You can use another molecule of pyridine to deprotonate. Electrons push up, and you get product. Okay, I'm running out of room. You have two byproducts. Okay. Apologize, I forgot to draw this one down here at the bottom. Protonated pyridine, call it pyridinium. Chloride. And what's here is another molecule of pyridine, protonated, with the phosphonate. It's this O- on phosphorus. Nice resonance stable, right? You could draw a resonance structure like this. You don't have to. Okay, but that's a weak base, good leaving group. Okay. That's POCl3 pyridine. Another way to convert, no, I'm sorry, that's two different eliminations. Okay, you can use strong acids like sulfuric acid, paratoluene sulfonic acid, and then you can use POCl3 pyridine. We can also look at 9.11, conversion of alcohols to alkyl halides with HX. Okay. So you cannot just take an alcohol and add X minus. You can't add like sodium chloride, for example. It just won't work. But you can take an alcohol and add HX and get RX and lose water. Okay, let's go over that. Same idea. We're going to see increasing rate of reaction from primary to secondary to tertiary. Okay, this is going to be driven by carbocations if possible. We're gonna have weak nucleophiles, the X minus. Okay, so for secondaries and tertiaries, we're going to say carbocation, and primaries are going to be slow because they're going to have to be SN2, but we're going to have a weak nucleophile. Okay, so let's look at primaries first this time. Take a look at a primary. It's got to be SN2 because we don't form primary carbocations, but the rate is still going to be slow. Let's show HI going to an iodide. Okay. The protonation will be plenty fast. Dissociation or protonation. Gives this intermediate. Now, you can't just lose water because this is a primary alcohol. This will come in here and attack from the back and give the product and kick out water. So it's SN2 with a proton transfer first. Okay, this is still slow because iodine is a weaker nucleophile, right? It's a weaker nucleophile because it's a weak base. But this can happen. You protonate, and eventually the I minus comes in there and attacks, forms this product. Notice this is the opposite of what we've been studying. Again, you could remove the water to help drive this process. You got a very strong acid, pKa of -7, that's going to drive this process. So let's look at a secondary or a tertiary, okay? In this case, a tertiary. Secondaries and tertiaries are going to be SN1, which means we're going to go through a carbocation. Use HBr this time. Protonation. Now what happens? Bromine cannot get in there. It's too sterically hindered, but you can lose water. So you get carbocation, tertiary carbocation. Br minus can then come in and attack, giving product. 1 with initial proton transfer. Very different conditions than we talked about earlier. Same rules apply to primaries and tertiaries. You can have inversion for this sort of chiral primary, right? We use deuterium to make that a chiral. This is a primary. You add HBr, and what do you get? You get inversion. Inversion of stereochemistry. Okay? Go through that mechanism. Same thing, you're going to protonate the alcohol and displace the water with Br minus. Okay? SN2 gives inversion. We look at a tertiary. Chiral center. Tertiary, 4 different groups. It's chiral, HCl. What do we get? We actually get 2 different products. We get the retention and we get the inverted. (50, 50). These are enantiomers. Get both products. Why? We go through carbocation. Cl minus attacks from the front or the back. Okay? So work through those, understand the stereochemistry. You can also have a carbocation rearrangement with this SN1 process. So let's look at this reaction. We have a secondary alcohol. We're going to treat it with HBr, and we're going to get a very strange looking product offhand. Br is not on the carbon we would expect it to be on. So how do we explain this? We explain it mechanistically. The alcohol attacks, gets protonated, dissociation. You push out the water first. You got to form carbocation to get a rearrangement. That's a good rule. You must form carbocation to get a hydride or an alkyl rearrangement. Okay, so minus water. What do we have? Carbocation, Br minus. Now the Br minus, we've shown it, again, up to this point, this is the same. We've been showing Br minus coming in and attacking that carbocation, but now it's favorable to go from a secondary to a tertiary carbocation. Let me redraw that over here. CH2 is now there, where the carbocation was, and there's that hydrogen. Now we have a tertiary carbocation. Okay, so that went right there. Tertiary carbocation, what happens now? Br minus is happy to come in there and capture, because now we have some stability. We went from a higher energy secondary to a lower energy tertiary, and now this is just going to sit there until Br minus comes in, and boom, that gives you a tertiary alkyl bromide. Okay, so hydrogen, these carbocation rearrangements are very important. All right. All right, for the sake of sanity, I'm going to stop there. So we'll do another reaction of alcohols, part 2 next time. And this will be plenty to get you started on chapter